All right, all done. So Pete, whenever you're ready.
Right, I'll see if I can share this. Hopefully you can all see that.
Yep, all good.
Cool. So I'm going to be doing a little talk. I mean, should we go straight into it, or do people want a couple of minutes?
I'm inclined to go straight into it, unless do other people want a break? Nope, I think we jump straight in.
Cool. Yeah, so I'm going to be doing a talk about 6DoF copters. So we're going to assume you've all seen that video, so you won't get to see it again. Firstly, I thought I'd sort of just go over a bit about what do we actually mean by degrees of freedom, and sort of what are we gaining with our extra going from what we have at the moment. So at the moment, this is just a quadcopter, obviously. So we have our 4 degrees of freedom that we can control our normal quadcopter in. So obviously we've got thrust, and it's sort of half a degree of freedom because we can only thrust up. You can't thrust down. So we've got thrust, and then obviously roll, pitch, and yaw, and they're sort of full degrees of freedom because you can roll both ways and pitch both ways. So that is our 4 degrees of sort of spatial degrees of freedom. So that's how we can move the vehicle about. And then to achieve that, we have like degrees of actuation. So we have 4 degrees of actuation on a copter. So obviously you've got your 4 motors. So in this case, our spatial degrees of freedom it equals our actuation degrees of freedom. And you'll see that's a bit of a theme. Ooh, I'm going the wrong way. So this is a tricopter. Again, we've got the same 4 spatial degrees of freedom that we can move in. Oh, and I should have said at the beginning, like, any questions, just jump in as we go and get stuck in. So that's our tricopter. And again, we've got 4 degrees of actuation. So we've lost a motor that we did have on our quadcopter, and we've swapped it in for a servo. And again, our spatial degrees of freedom equals our actuation degrees of freedom. And then a bicopter, so we've got the same thrust, roll, pitch, yaw, and we've swapped another motor for another servo. So we've got 2 motors, 2 servos. So we've still got the same amount of actuation degrees of freedom. So you'll see that's a limit. We need at least the number of actuators as spatial degrees of freedom. But of course, many times vehicles have more actuators. So this is an octocopter. So we still only have 4 degrees of freedom, even though we've got 8 actuators. So in this case, we've got more actuation than degrees of freedom that we can move in. So why would you do that? Surely, if you can only use 4 motors, why would you not just use 4? So it gives you redundancy. So because we know we need at least 4, if we've got 8, that means, you know, theoretically we could lose 4 motors and still be able to fly. Obviously, it doesn't work out like that in practice. There's packaging reasons you might want to do that. Maybe you need more. You need to get it all compact, or you can't get the enormous propellers that you want to build your enormous vehicle. So you need to use more smaller ones. And then response time. So if you sort of small propellers change direction and spin up and down faster than huge big ones. And response is also important for, like, on our tricopter and bicopter, like the servo response makes a big difference, and the servo won't respond nearly as fast as the motors will. So maybe you're better sort of choosing a different combination, even though you're then an over actuated system. And interestingly, you can in fact get under actuated systems. So this is a bit of a tangent, but I think it's quite interesting. So you can trade off static stability. So because we don't match our spatial degrees of freedom to our actuation degrees of freedom, you can't be statically stable. So you can't hover in one spot anymore. You have to move. So if I was to jump and you took a picture, you would know I can't hover. I'm not hovering in space. I'm dynamically in space. So you can sort of get more than you put in by making a system that's dynamically stable. You can punch above your actuation degrees of freedom. So both of these examples constantly spin. So it's the Lockheed Samurai. So that's one motor, one servo, and it can move about in 3 degrees of freedom. So it can go up and down, and then it can translate, left, right, forwards, backwards. But you can't, you can't control yaw, obviously, because it has to spin the whole time for it to work. And then another one that is quite interesting, and it is sort of quadcopter motor failover. So if you were to lose a motor on a quadcopter, you can transition into this dynamic stability by spinning the copter round, and then that might be just enough to get you home. But obviously it's not ideal. But as a sort of fail-safe, it's really handy, and it's fantastically cool as well. So that's a sort of overview of degrees of freedom. And of course, ArduPilot actually already does 6 degree of freedom vehicles. So ArduSub, this is the blue ROV2, and you can see it's got some thrusters here for going up and down, and then it's got 4 thrusters, front, back at angles like this. So it can translate without rolling and pitching. So it's we have actually been doing 6-DOF vehicles for ages in ArduPilot. So to make a 6-DOF vehicle, we know that we want it to be sort of statically stable. So we know that we need more than 6 motors. So 6 would be our minimum number of, well, not motors, 6 actuators. Obviously, you could use a fewer number of motors and have them on tilts or use flaps or something. But if we just want to use motors, we need 6 motors for static stability. And then this gets us our same thrust, but in this case, to be a true 6-DOF vehicle, you need to be able to thrust both up and down. So that's sort of an enhancement over the existing copters. We need to be able to thrust in both directions. And then obviously roll, pitch, and yaw are exactly the same. And then our 2 additional degrees of freedom, so this is what takes us from a normal 4-DOF copter to up to 6-DOF, is these forward, back, and lateral, left, right thrust. So we can then move in our full 6 degree of freedom space. And as I said, we know we need 6 actuators, and to be a true 6-DOF vehicle, our actuators need to be able to thrust in both directions. So at the moment, ArduPilot only really understands 4-DOF vehicles. And if you think about sort of how ArduPilot sees the vehicle, the main navigation code and even the attitude control code doesn't actually know very much about the vehicle. It doesn't know if you've got a quadcopter or a tricopter or a bicopter. It just knows that if it wants to go forward, it should pitch forward. That's sort of baked into the code at quite a low level. So it just says, I want to go a bit forward, I'll rotate my thrust vector. And I think the sort of key to understanding how the 6 degree of freedom vehicle works is to sort of imagine you've got X-ray sunglasses and you can't see the vehicle, but you can see its thrust vector. So you can just imagine that the thrust vector moves, and don't think about what vehicle the thrust vector is coming out of. So because we don't really care about what the actual vehicle is, we can just imagine the thrust vector moving. So we can, on our 6 degree of freedom vehicle, we don't actually have to move the thrust vector with the vehicle. We can just pivot the thrust vector, but the vehicle stays level. And as I say, this is really the key concept to understand how this works, is that we don't have to move the vehicle to move the thrust vector, and that assumption is baked into basically every multi-rotor ever. But on this vehicle, we can break that assumption. But as I say, the underlying code it can't tell. It just thinks you're still a mystery multi-copter that has rotated its pitch, its thrust vector. So really, the 6 degree of freedom vehicle, at the moment anyway, is just pretending to be a 4 degree of freedom copter, and only the new 6 degree of freedom attitude control library and the AP Motors 6 degree of freedom code, those are the only 2 libraries that actually realize that, oh, I've not actually pitched the vehicle, I've just moved the thrust vector. So that, because nothing higher up in the code actually needs to understand that, which means that auto and loiter and RTL, they all just work automatically, basically because they're using roll and pitch as a proxy for rotating the thrust vector, and then we just sort of back calculate. We remove the roll and pitch and rotate the thrust vector as the same amount, and actually results in some quite interesting stuff if you go and look at like position control logs when the vehicle's upside down, because like the target velocity will be, it's still in body frame, so the target velocity is actually in the opposite direction to the target position, but then it all gets rotated back. So the high level code does need to understand, but it's all a bit weird because sometimes it looks like the vehicle's trying to fly away from where it's getting to, but it's all upside down, so it comes right in the end. And of course, because we can rotate the thrust vector relative to the vehicle, it means we can just rotate the vehicle and keep the thrust vector pointing up. And again, the higher level code really doesn't need to know. What it doesn't know doesn't hurt it. So we just carry on pretending to be a normal 4 degree of freedom copter that is perfectly level or pitched forward if we're moving forward. As I say, really, that sort of step that we take, we just don't tell the higher level controllers, and it all just works, which I think is sort of the I don't know, it's the key assumption as a key jump that we have to make that makes this all work very simply without having to like completely reprogram the position controller and completely change our PID system and things like that. So we just pretend that we're just a normal copter, and we can actually get away with it. And it of course it brings a few constraints, but actually the constraints are not that bad, and we'll cover that a bit at the end. So in order to set this up in ArduPilot,
Hey,
it's
Peter.
all in. Hey,
Peter, it's Bill. Hey, so now how have you changed your controller, like on the controller side, like the person making the control inputs, has their controls and what they mean or what they do change?
so
does lateral stick still mean rolling the aircraft, or how does that change?
So at the moment, lateral stick means we re-rotate this imaginary copter that the vehicle's pretending to be, and so we just move the thrust vector. So at the moment, if you were to take off and just fly about like you would fly a normal copter, the vehicle would then stay completely level, and it just sort of shoots sideways in a very weird and unintuitive way that takes a little while getting used to. Does that cover your?
Go ahead and say that last part again. I'm not sure I caught that.
So it just stays completely level. So if you were to have your X-ray sunglasses that could see thrust vectors, it would look exactly the same. It's just the vehicle stays level and the thrust vector rotates. So you pitch forward, the vehicle doesn't pitch forward, the thrust vector pitches forward.
Okay, so now you're basically controlling translational rate with with the elevator and aileron sticks.
Yeah, exactly right. Exactly right.
Okay.
And as I say,
right.
if you had magic sunglasses that could see thrust vectors, you wouldn't be able to tell the difference. It's just we can unlink the thrust vector from the vehicle attitude.
Cool, thanks.
Yeah, so this is how you set it up. It's all in master now, 4.1 dev. The only constraint is that you must have a scripting capable flight controller. So you just need at least 2 meg of flash space. So the frame class is a new frame class 16, and in the parameter description, it's called 6DOF scripting. So basically, because these frames are so complicated, I decided there's basically no point in having, like as we do for normal frame classes, we have like Copter X and H and a whole bunch of pre-existing ones that you can just pick from. But because these vehicles are so weird, basically we would never get the defaults right. They wouldn't apply to, they wouldn't be universal enough to apply to everyone's vehicle. So you have to generate your own mixer because they are very specific to vehicles. So we use scripting instead of adding, hundreds of params. We use scripting as a nice, easy way to load a lot of data into the motors library, so it understands the shape of the vehicle, as it were. So you use this new motor 6DOF add motor command in your Lua script, and this. How many lines is this? 7 lines is what you need to set up the vehicle. So you have a little Lua script, it loads in all this data, then it sets up the motors, and then it goes away. So you don't, the Lua script is literally a knit thing. It just sets up the motors and clears off. So we use this function, add motor, and then we've got motor 0, so that's the first motor. And then obviously we go 1 to 5, and brilliantly, the motor number is 0 indexed. And then at the end, we've got testing order, which is 1 indexed, just to confuse everyone. So in almost all cases, you want the motor number and testing order here at the end to match. Except we've obviously got that index offset. But if testing order is a bit of a, that's just like if you go in mission plan and go test motor A, that's these numbers at the end of the order. But I think in almost all cases, you just want them to match. So that's the sort of setup stuff. And then we've got 6 numbers, which sort of define the contributions of this motor to each of our 6 spatial degrees of freedom. So we've got roll, pitch, yaw, throttle, forward, and then right. So that's our attitude factors, and then our sort of direction factors. And then the last bit here is just a Boolean true false. So on my vehicle, all the motors are reversible. So they can thrust in both directions. So that just tells ArduPilot that no throttle is at 1500 PWM instead of 0, or rather 1000 PWM. So you can actually do, if you wanted to, of course, I've not tried it, but you could do a combination of reversible and not reversible motors and things like that. And of course, you could just set up a normal quad with this exact mixer. You would just have zeros in the forward and right column. So these last 2 columns would all be zeros. The thrust would all be 1s, and then you'd have your like roll, pitch, and your factors just as you do in the normal AP motors library. Oh, and it's worth mentioning as well, you can do custom normal frame types in almost this exact way. So it's a slightly different handle, and then you don't give it you just do the angular factors. So if you've got some normal 4 degree of freedom multi-copter, you can actually set up the motors with this same, or rather a very similar method. So we tell motors that it has 6 motors and this is the position they're all in. and then we tell it that it should now init, and it should have had 6 motors. So we just tell it to init and make sure it has had 6 motors, so we don't, accidentally forget to load one and then tell it to init. So that is how you sort of set up and you configure your custom frame. And then once you've done that, you can then use a second Lua script to sort of change the attitude of the vehicle. So because ArduPilot does only understand 4 degrees of freedom, there's sort of no way to with normal inputs that ArduPilot understands, there's no way to control these extra 2 degrees of freedom that we have. And unless your transmitter's got an extra stick on it over here, like you can't input stuff. So instead, I went for just making it accessible by a script. So first of all, you can use this set lateral enable and set forward enable. So if you set these both to false, your 6 degree of freedom vehicle changes back to a 4 degree of freedom vehicle. The thrust vector is always up, and it rotates the vehicle again. And although it doesn't make much sense for a 6 degree of freedom vehicle, you could, for example, do a 5 degree of freedom vehicle that could, say, hold its pitch level whilst moving forward and backwards. So you would set forward enable to true and lateral enable to false. So you would still have to roll to go sideways, but you could go forwards and backwards while staying level. So you can do, you can sort of drop down from 6 degree of freedom if you want to in a script. And of course you can do this based on like an RC switch, or I'm in auto mode, I want 6 degree of freedom. I'm now in stabilize, I want this other thing. So making it accessible to scripting lets you do lots of clever stuff. And then of course you can set this offset roll and pitch. So that's how we control the vehicle in its roll and pitch. So as I say, because we can't do it from the sticks, we use a script. And of course you could use the script to bind it back to the sticks if you wanted to. And this offset is then just directly applied to the target attitude. So the attitude controller just adds it on to what we're asking for from ArduPilot, and it all just works, which is quite satisfying, that we can just add sort of a roll and pitch offset, and the existing attitude controller just deals with it. So in my demo videos, I was just doing sort of roll equals less roll plus some number, so it just rolls at a constant rate from a script, and then you have a little switch to turn it off. So there's also this bit of a trap here, which is ATC angle boost. So you have to turn this off because there's a singularity at 90 degrees. So if you if you're happily turning your 6 degree of freedom vehicle upside down with angle boost turned on, when you go past 90 degrees, the throttle goes away because there's this singularity in the way that angle boost works. So you have to remember and turn that off. And because when we're in 6 degree of freedom control, we actually ignore these roll and pitch offsets. We don't pay any attention to those when we're setting our thrust vector. We just go, oh, well, thrust is always up. So we rotate it, or rotate the thrust vector such that thrust is always up, which means that in theory, you actually don't need attitude control to be able to fly your 6 degree of freedom vehicle, forwards, backwards, left, right. So it's a bit like those sort of non-statically stable systems. So theoretically, you can turn your roll pitch, your PIDs to 0, and the vehicle will still fly around fine. But of course, in practice, it'll build up quite a big like roll rate or something, and you'll end up spinning really fast. And then the motors can't change direction fast enough, and it'll all go wrong. But it's quite a nice way to just confirm that like all your rotations are correct. So I did this as a sort of a way to test it, and I thought it was quite fun that it even works. that you can actually fly the vehicle with no attitude control. So you saw my big matrix of numbers. So how do we come up with those numbers? So there are a few considerations. So all of the existing ArduPilot mixers don't consider that motor torque and motor thrust might be acting on like more than one axis. Or so on a normal quadcopter, pitch is controlled by a change in thrust only, roll is controlled by a change in thrust only, and yaw is controlled by a torque only. So you don't have to deal with thrust and torque contributing to one axis. So that is a thing that makes it a little bit more complicated. And of course, on a sort of normal vehicle, you can't do roll, pitch, or yaw if you also want to do zero throttle. You have to pick and choose a bit more. So you might have to, and we actually do this at the moment in the code, which is if you're trying to pitch really hard and you've got a big attitude error, it'll bump up the throttle. And of course, on a 6 degree of freedom vehicle, we don't necessarily have to do that, because we can roll, pitch, and yaw whilst applying no thrust vector if we wanted to. So the key thing for understanding this sort of combinations of thrust and torque to act on one axis. So I think that the clearest example here, and you can see this is a sort of representation of an example of motor layout. So it's just a sort of, if you imagine a sort of origin, all these lines are at a sort of 90 degrees in space. And then at the end of each sort of axis here, you've got a motor, and then at the other end of the axis at 90 degrees is a second motor. So pitch would be sort of along this axis, so this between motor 1 and 5, that would stay in the same plane, that would be pitch. And you can straight away see that motor 1 contributes to pitch by thrust, but motor 5 contributes to pitch with its torque. So here the motors are colored for rotation direction, although it doesn't make a huge difference what rotation direction you pick, so long as they're not all the same in this particular layout. Of course, in other motor layouts, it might be quite different. So first, the key thing was to benchmark what our thrust and torque values are. So for this, Matt has built a lovely thrust test stand, and you can see here it's got on this reversible propeller that I used for my vehicle. So we did some testing to benchmark that, and this Matt's fantastic stand, and you'll have to wait until tomorrow to hear a bit more about that in his talk. So then we got this lovely data set. So the first thing, I was quite impressed with this. We, this is thrust versus throttle for forwards, and then we reversed the motor and reversed the prop so that the sort of thrust was in the same way, but the prop was going backwards. So actually, it is a 3D propeller. It truly is. That it lines up really well in both directions. So it's nice and symmetrical for thrust, and actually that's quite important for how the code works at the moment, that it is nice and symmetrical. And then again, torque and current and voltage. So first, the key thing is that I was quite impressed how symmetrical this 3D propeller is, and I suspect you have to be a bit careful that they are nice and symmetrical, because some of the sort of ones you might want for sort of multi-race quad flying, they're mainly meant for the right way up, and sometimes you might thrust backwards a bit. And then we benchmark the maximum thrust and the maximum torque, so 1.2 kilograms of thrust and 0.01 kilogram meters of torque. And of course, because we've got lovely thrust test data, you might as well calculate the expo. So a little bit unusually, so typically you would use a spin min and spin max, but because our motor has to reverse, your spin min has to be 0, so that it smoothly reverses. You can't jump from 10% to -10, so your spin min has to be 0, and then we just do a best fit on the expo here. So this is a Mott thrust expo. I did this in MATLAB, but if you go and look on the wiki, there's a spreadsheet, a Google spreadsheet that will help you do this. So then a bit of a MATLAB file to do all the hard work. So we give it the position of all the motors. So that's sort of the center of the motor where the thrust vector would be acting effectively. We give it the direction of the thrust vector. So like this thrust vector would be 0x, 1y, and 0z. So it's just unit thrust vectors to sort of define what direction the motor is pointing in. We give it the motor rotation direction. So I think here green is clockwise and red would be counterclockwise. So that rotation direction just matters because that is the direction, or it defines the direction that the torque will be applied in. So then we take our maximum torque and thrust, and because we've done that expo calibration, we can assume that the thrust is linear. So we give it a throttle of 100%, it will make, say, 10 force units. And if we give it a throttle of 50%, it will make 50 force units. So that linear relationship that this expo lets us assume is key to calculating the mixer properly. And of course, it also means that the change in thrust between 0 and 5% is the same change in thrust between 95 and 100, which is key to getting the PIDs to work across a whole range of throttle values. So then from these positions and vectors and the max thrust and torque, we assemble a matrix to go from roll pitch yaw throttle forward right inputs to the motor outputs. So you would give it, say, a throttle input, and it would go, oh, you need to apply some throttle to, say, 1, 2, and 3. And of course, we can also go back the other way with the same matrix. So you can say, oh, what will the vehicle do if I give it 100% throttle on motor 5? And obviously, intuitively, you can say, oh, well, it'll probably yaw round and it will move to the right, in the negative right direction. So we can intuitively say that for motor 5 because it's nice and lined up with one of the axes. But obviously, all combinations of that is nice to be able to just automate it. So this is the sort of naive mixer that gives you. So you could sort of intuit this as well. Like you can straight away see that throttle is only motor 1, 2, and 3. They have some Z component in their thrust vector. Motors 4, 5, and 6 don't have any Z component in their thrust vector. So if we ask for throttle, they won't do anything. And again, so for right, you can see motor 5 that we were just talking about, that has a 1 in its right motor factor here. So that is 100% going right. And then yaw is quite an interesting one because you can see that the top motors, all the thrust vector acts directly in yaw. So we have the top motors, which is 4, 5, and 6 at the bottom on this table. So we have big numbers here because the thrust is acting to yaw the vehicle, but motors 1, 2, and 3 is small numbers, about 10 times less. And that's because it's the motor torque that is acting to rotate the vehicle. So I think this is sort of quite an intuitive table. And for things like quadcopters and fairly straightforward layouts, like you don't even need to do all this maths. It's all very intuitive and you can just write the numbers in. But obviously for these 6 degree of freedom vehicles, you need a bit of help. Well, I certainly needed a bit of help. So we I came up with this little sort of mixer to help. And of course we now have the calculation to go from inputs to motor outputs and back again. So we can see, using that sort of naive mixer, if we input roll, so these graphs are each for an input of like -1 to 1. So we got a graph for roll, a graph for pitch, a graph for your throttle forward right. So if we input only roll, we use the matrix. We go, oh, well, I've got 1 in this column, 0, 0, 0, 0. So we go 1 times 0.2, 1 times -0.5. So you can see, you know, that's minus 0.5 there. So that is what this graph is. So we put in a roll, we go to what our motor outputs would be, and then we go back through the same matrix and we come back to what does that then make the vehicle do. So in fact, if we put in a roll, you can see actually we also get some forward input. And I think perhaps the most intuitive one of these is pitch. So if we go and look back at the sort of diagram of the vehicle, you can see to pitch up, we would throttle up this front motor, and that has some thrust vector in the forward direction. So we would move a bit forwards as well. And you can sort of see that for each of these different axes, it's not a very big contribution, but another quite intuitive one, I think, is throttle. So on throttle, we already know we only throttle up these bottom 3 motors. And you can see that we have 2 going in one direction and 1 going in the other direction. So obviously there'll be, if we throttle them all up equally, there'll be a net, or there'll be a torque difference of 1 motor's worth of torque. So we're bound to yaw a little bit when we throttle up. So that's sort of what this graph, or these graphs represent. And you can see if we put in roll, we get sort of 58% roll and minus 20% forward. So this is all the cross coupling between axes. And of course, because we've now got a nice error function for this problem, basically, we can optimize that. So of course, we've got 6 motors and 6 sort of known values. So you could also just solve the equations. But if I wanted to then do 7 motors, you can't solve the equations anymore. So we've got a nice error function here. So I just used a basic, an optimizer, a particle swarm in this case. So I just use that as the error function, and we go, for roll, I want only a roll output. So basically we bake into the mixer some feed forward between axes. So the mixer understands that if it puts in roll, it should also put in like minus 20% throttle to exactly cancel out that throttle. So it's basically feed forward between axes, except we bake it right into the mixer so that you don't have to like obviously we could add a bunch of parameters for feed forward between axes, and you could go and calculate them all and tune them all up in the like as you're tuning the vehicle. But we can jump sort of straight there by baking it right into the mixer with this optimization. So that is I think a sort of a key thing, and it sort of helps the, well, like it will totally still fly on this naive mixer, but you get more cross coupling between axes, and you can't turn up the PID controllers as much because they all sort of they all get in a fight. Like your roll will be trying to do something, but that'll affect pitch. So you end up, all your PID controllers are fighting, and because of that, you can't turn up the gains as much as you would like. But if we do this nice optimization, we remove all that cross coupling right in the mixer, and then the PIDs no longer get in a fight with each other, and we can turn up the gains a bit more. So this is our sort of corrected mixer. So you can see we've no longer got zeros in this for our top motors in throttle. So even though they haven't got any thrust vector in the up down direction, they have a little bit of throttle come on when you try and go up. So that is just to cancel out that one motor's worth of torque. And of course, it's the same. I think it's so intuitive to sort of understand for lots of these axes, but it's all the same idea. And then, so the only other thing we then do is we scale it to 0.5. So the roll pitch and yaw are all scaled, so the maximum number in here is an absolute value of 0.5. And then the throttle forward right columns are all scaled, so the maximum number is an absolute value of 1. And the scaling really it's not that important from like a one-off point of view. Like all that matters is that this number times whatever your PID's output is the same. So we could have 10 in here, and if we divided the PIDs by 10, it would all fly exactly the same. But if we apply this scaling in the mixer and it's consistent, so if you go and fudge the mixer, you still have a maximum scaling of 1 here and 0.5 for roll, pitch, and yaw. It makes the PIDs still apply roughly the same. And the other reason is that we use a maximum of 0.5 for the normal Copter mixer, and by using 0.5 here, the default PIDs apply reasonably well. Obviously, they're not perfect, but it gets us so the PIDs are in sort of the recommended range of the existing parameters, which is quite nice. So that's how we calculate the magic mixer, and that's more or less all there is to it. It's the sort of thing that one assumes is very complicated, but basically there's just the one sort of key thing to the code, which is this unlinking of thrust vector and attitude. And once we've unlinked those, suddenly you can do all this other stuff. And actually, the patch to enable sick stuff is not as big, and it's not as complicated as you might imagine. We just trick the higher level codes into thinking that we're still a 4DOF vehicle, and then just deal with the extra degrees of freedom in the mixer and in the attitude control library. So there's, well, is there any questions on what we've done so far before we cover a future work? Everyone's baffled.
Oh, it's pretty cool. It's pretty cool.
It is very cool.
Yes.
Yeah, I hadn't realized that optimization at all when I sort of saw the previous videos and things. That's really fascinating, the way you counteract the effects in the other axes. And that immediately just made me start to think of quad planes. And I now see you've got a photo of a quad plane up there, a very, very old quad plane. So yes, I'm starting to get ahead.
Yeah, so go for it.
No, go ahead. So obviously you're going to start thinking about, actually doing this extra half axis on a quad plane, and also with tilt rotors and things as well. That also all dynamically.
Yeah, sure. We might not necessarily need to. I think we're getting to spoilers for Tim's talk tomorrow, but we'll often for you don't need to do the clever mixer, because all this cross coupling is just like a factor of like either sine or cos of your like tilt angle. So you don't need all this clever stuff, because you know what the values will be, because it's just a sort of one axis rotation. So yeah, future stuff. So actually, I think like proper 6DOF vehicles, very cool, but probably actually not fantastically useful in the real world. So I think, and actually it's quite a bit harder to like the fixed off vehicle is essentially completely unconstrained by like angle limits and things like this. And I think what will be more useful and actually a little bit harder to implement is things like this copter. So I went and found, this is from a DIY drones from 10 years ago or something. It's just a copter +1. So something like this is actually, I think, a little bit harder to deal with because it does have constraints. Like at some point, for example, you would be at full throttle on your extra forward motor and you would want to then lean forward a bit to go faster, or this motor isn't reversible. So if you can go forwards perfectly level and use this motor, but if you want to go backwards, you can't use this motor and then you have to pitch the vehicle. And I think sort of dealing with constraints of actuators that we would get on things like this actually makes this whole code or dealing with it all a whole lot more complicated than the fixed off vehicle that is just completely unconstrained by that stuff. Like you want roll 180, go for it. We can do that. So I think dealing with these constraints will be quite a bit of extra work, but I think that is really where the benefit of these extra degrees of freedom will be. Like being able to roll and pitch, completely upside down is not that useful, but maybe you want to be able to just translate whilst level, and we get a bit of extra degree of freedom, but not that much, and maybe only in one direction. And of course, what does this vehicle remind you of? 4 motors in one axis and 1 motor in another axis. Oh, it's just a quad plane. So we can potentially use the same stuff with a quad plane, and quad plane has a bit of an attempt at this with its forward throttle gain, but we could take advantage of that a little bit more. So the other thing is, like at the moment, copters assume all your motors are exactly the same size. So you've got this 1 expo value, and for these fixed off vehicles or things like this quad plane, maybe you would want some big rotors that you do in your normal orientation, but then I want to pitch up a bit, and you have some smaller rotors that you wouldn't use as much, or you might want to mix and match motors sizes a lot more than you would on a normal multi-rotor. So maybe we would need multiple expo values so we can deal with motors of a different size. And you might also want like multiple maximum thrust levels. So for example, you might have a copter that is largely optimized for flying the right way up. So it's got nice efficient propellers for that orientation, but you can also fly upside down if you like. But now your nice efficient propellers are not so efficient because they're optimized for one direction. So you have to deal with them having like asymmetric thrust depending on the rotation direction and things like that. So again, sort of the first 2 things are sort of to better deal with constraints of actuators, so we can use them on more practical vehicles. And again, for more practical vehicles, at the moment, the only vehicle that has flown with this has used 6 reversing motors. And that is quite a big constraint in that you can only get like true 3D propellers in a sort of 5-inch size. And if you go much bigger than that, even if you could get the propeller, suddenly reversing takes too much time because your inertia goes up in your propeller and you just can't reverse it quickly enough to be able to control the vehicle. So again, actuator constraints, and at the moment it's theoretically possible to do non-reversing motors, but it's never been tested. So better mode support would be another one. So at the moment, for example, if you just switch into acro mode, it just goes, oh, I'm just a normal forward off copter. So for example, if you're rolling upside down and you switch into acro, bad things will happen. You can still fly in acro. It just doesn't understand those extra degrees of freedom in the same way that like stabilizer, hold, loiter, and the higher modes do. And I think another big hurdle to this work is that although the vehicle can totally do crazy stuff, it's very difficult to control it in an intuitive way. So as I say, you'd need an extra stick on your transmitter, and you'd have to, be able to fly with, your eyes pointing in different directions and stuff. So what we need perhaps is something, a bit like Copter's drift mode or something, where the extra degrees of freedom are just sort of dealt with in quite an intuitive way. And because we can control them with scripting, we don't have to do that in the main code. So we can prototype that all in scripting and try and sort of take advantage of the extra degrees of freedom that we gain without making it hugely complicated to fly or super difficult to program missions. So I think Peter actually had a good idea in this direction. So for example, we could use the gimbal controller to control the roll and pitch. So for example, you could do like a region of interest and the copter would fly about in the circle or whatever. And then the roll and pitch control would be done a bit like a gimbal. But of course, that only really works if you're in auto modes. Otherwise, the pilot will get very confused. I've taken to flying this my one in simple mode, because then it doesn't. You have to sort of unlearn. It took me quite a few flights to get used to it, to unlearn keeping orientation and go back to like not caring about the orientation of the vehicle. But it makes it a bit easier to fly, and you can't really lose orientation anymore once you've sort of unlearned normal flying. So another enhancement would be true 6DOF position control. So at the moment, like we're still pretending to be a 6DOF copter underneath, a 4DOF copter rather. So for example, the 6DOF vehicle can thrust downwards, so you can do faster than 1G descents if you wanted to, while staying level. And that is something that the higher level, like position control, the Z controller, they just don't understand that. They don't think it's possible. And another one, at the moment, you can only go sideways with the same thrust as you have downwards. And that's just because we're pretending to be this vehicle that is just a 4DOF vehicle with its thrust vector. So in reality, we could go sideways at full throttle whilst descending, but it's not possible to do that the way it is currently. But actually, doing greater than 1G descents and shooting sideways at huge speed, even though the vehicle can do it, is perhaps a bit of an edge case of would people actually use that? And I suspect dealing with that stuff properly we'd then have to do the massive rewrite of position controller that basically our pretending to be a 4DOF vehicle has bypassed. So to sort of do it properly, there'll be quite a lot of work there, but whether it brings enough benefit is sort of another question. And then I think something that this could work really well is VTOL stuff and quad planes, because as we saw here, they already have the motors for this. They for the most part, they're already set up for it. And I think a really cool thing that jumps to mind that we could do, so we can now control the vehicle's attitude independent of its position. So a quad plane hovering in the wind, we could now tilt up while staying in the same position to climb. So we can take advantage of the wind and the lift over the wing. So we can tilt the vehicle up, change its attitude without moving backwards to climb. And then we want to descend to come down. And that's actually something that quad planes struggle with quite a lot. So people will often find it quite hard to land if it's windy, because it's got so much wind under the wing. So we could now, you could have a little script that changes the pitch of the vehicle so that the throttle is always at the same level or something like that. So we can really take advantage of that. And for things like transitions as well, you could now say, I'm going to be 5 degrees pitch up for the whole of my transition. And then you should be able to transition a bit quicker. So things like that, I think. And again, it's not full 6DOF control. Maybe for quad planes, you only need to sort of unlink your attitude from your thrust vector just for like 10 degrees around 0. So you can just do that angle of attack control in the hover. And I think that's where the sort of real benefit of this stuff will come in for many more people than than the full 6-DOF silly copters flying upside down stuff, even though that isn't great fun. So I think that's basically the conclusion of my 6-DOF ramblings. Any more questions?
Yeah, the stuff about that you've just been describing about, quad planes optimizing that wing angle. Len and I have already been discussing that a bit when we were doing some of the ship landing work. We were looking at exactly that and trying to do a bit of a controller in the quad plane code for doing that, because it's one of the big problems at the moment is that it can be that it can be difficult to land, but it also can be that if it tilts down too much, it ends up, you overload the motors, the vertical motors get too hot. So you've got a whole lot of these extra constraints, but the speed of the throttle on the forward motor can be a real problem. If it's a petrol forward motor, it may respond fairly slowly, especially at low throttle levels. And so you have this sort of extra dimension, if you like, with you're not as fast in some axes as others. It's very asymmetric.
Yeah, I think dealing with these sort of actuator constraints is going to be one of the big hurdles for that stuff.
Yeah, indeed. But very worthwhile to try and solve it.
One of the, if I had been a little less tardy with my preparation and didn't have to swap with Randy on my talk, I wouldn't, a bit of a spoiler for my talk is that one of the changes that will go into 4.1 is multi will be running off thrust vector plus attitude instead of roll pitch yaw for 4.1. So the attitude controller will take in a target thrust vector and a heading, as opposed to roll pitch yaw, which obviously for you is very easy to extend to thrust vector and roll pitch yaw, or thrust vector and attitude. And so, yeah, it has a lot of big advantages for multi-rotors actually doing it that way because of the paths linking various thrust vector targets, as opposed to using Euler angles to link to specify thrust vectors results in poor paths between those angles, especially when you're starting to get attitude errors, in particular yaw errors in that. And because of what Tridge says is yaw, the yaw axis is operating on a different time scale to roll and pitch. So by including a attitude change to link to target thrust vectors using yaw is suboptimal because you have to wait for yaw to catch up. And so in the attitude controller, we define roll and pitch based on our current yaw, not our target yaw. And even to try and account for that, but it only accounts for it somewhat because of the paths that we attempt to follow. So yeah, so all of this stuff is hopefully going to sort of come into its own, where we can elegantly split out the attitude controller for like things like boost throttle. For you shouldn't be in there. You should be able to use most of the attitude controller, but the 3-axis thrust vector thing, multi-rotors really only need one of that. So hopefully we can find a way to slice out. If we get that representation right, hopefully we can find a way to slice out where you can simply override aspects of multi, or I'm not the programmer here, but the way it's structured, we should make it very easy for you to or for these various vehicles to be accommodated. Things like the what you're talking about with the forward facing thrust, for example. You've only got forward facing vectors for quad planes. It shouldn't be too difficult to say if we're wanting to, if the thrust vector goes past, goes to negative pitch angles, we go to negative pitch angles. If it goes to forward pitch angles, we increase the forward motor and things like that. So I'm going to I hope that there'll be a number of people helping me sort of work out how to do this from a code structural perspective. But the basic architectures of the various controllers have sort of been set up to try and facilitate that step. Hopefully maybe over the next 12 months, but we'll see how all that comes together.
No, that sounds great, and we'll be able to sort of remove my. It won't have to pretend to be a 4-dot anymore. We can just use the thrust vector directly.
Yeah. There's always going, as you say, there's always going to be the human interface, which is the challenge. We do have 10 fingers, so we could handle 6 maybe, but that most of the controllers don't come with the extra. One of the other things that I thought was interesting about the whole 6-DOF thing is the motor mixer. You've used a pretty simple sort of matrix multiplication to work out what's happening, but I assume you haven't sort of went in and done a lot of your saturation effects.
No, yeah, I'm done with that at all.
Axes prioritization. But it's one of those interesting things where with your 6-DOF vehicle, if it loses an actuator and you have simply prioritized the thrust vector over the attitude actuator, like the thrust actuator sum over the attitude actuator sum. So you basically reduce the attitude or change the attitude actuator to ensure you get maximum thrust vector command control of your attitude. It will just rotate, maintaining that vertical thrust vector until that actuator sort of sits at the bottom, like, if you know what I mean. If it's not, or it just tumbles and it goes zig 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 on the bottom and the rest of the that thrust vector is still just not affected pointing vertically. So yeah, that was one of the other things, like the absolute nightmare to do that thrust prioritization on 6 axes, but it would be an interesting problem to solve.
Great. I don't think we have any questions on the YouTube or anywhere else.
One thing I just want to mention was, they do have those 6 degrees of freedom joysticks, right? Where you can actually like pull them up and down. It's like a regular joystick with a roll and pitch, and then it's actually got yaw as well, and then you can. It's got a vertical.
I've only got a 4 degree of freedom brain now. That's the trouble at the moment.
Really looking forward to playing this after having played a lot of a game called Descent, which is a 6-DOF game. So looking forward to playing with one of those 6-DOF copters with the same control system I used in that game, which is simple keyboard stuff.
And I'm looking forward to watching you playing with the 6-DOF copter and laughing from the sidelines while I take video.
And I'm looking forward to seeing the crash.
It does need lasers though for that game.
Right. I don't think LiDAR is quite the same. Yep. Oh, good. So this is absolutely fantastic. Thank you very much for the wonderful talk, Pete. Really enjoyed it. And you've got some very complimentary comments there on the from the live stream. And Ian seems particularly keen from MadTech, particularly keen on your vehicle.
Oh,
so,
I mean, we'll have to. He's only down the road. Once we're out of lockdown, we'll have to go and
go and give
a live demo.
Yeah, you should definitely do that. Put something up on his YouTube channel. Excellent. So, so that brings us to the close of this evening's talks. And so it's been absolutely a brilliant day. And we've now got the final day of the conference starting tomorrow morning, Canberra time. And some of you, if Europeans, might decide to sleep in, and others of you are going to get up early for your talks. And I think, Pete, you might be one of those that needs to get up early, given we've got Tim from Transwing talking at 9 a.m. Canberra time. So my apologies. That was actually a bit of a scheduling stuff up to have you last on the previous evening and being part of the call tomorrow. So my apologies for your sleep patterns over the next few days.
I know, power nap. Going back to bed for a few hours now. That's the plan.
Excellent. So, in the morning we've got a series of great talks lined up. We've got Tim Whitehand on the Transwing, Bill Geyer giving a helicopter update, Leonard giving the infamous or famous S-curves, the final twist
last
talk, and then Michael with a mission planner update. And finally, we'll have a few short presentations. Now, we will have a bit of extra time at the end of the short presentation. So if anyone wants to give a lightning talk and has, something has during the previous talks have inspired you to give like between a 2-minute and a 5-minute presentation on something, then feel free to put your hand up and let us know, and we'll add you into the schedule. We had lightning talks to great effect in some past years when we had the face-to-face conference, but we didn't really think about them properly for the online. And I think we should think about that. So and add any in if somebody has an idea. So wish you all a very good night and sleep well, and look forward to talking to you all in about 11 and a half hours time.
Thanks, Robert. Good night.
Later.
Yeah.
Good night.
Thanks.
See you later. All. Good night, or have a good day.
Good day. Good night.
Yeah.